Hello everyone and welcome back to the Repair and Installation TV channel. The construction of large hydroelectric dams is a complex, multifaceted process that demands cutting-edge technology and modern equipment. The role of machinery and contemporary devices is crucial in various stages of dam construction, from initial site preparation to final operations. This section explores the significance of these technologies, highlighting their impact on efficiency, safety, environmental considerations, and overall project success with specific numerical examples to substantiate the points made. One of the most significant advantages of modern machinery in hydroelectric dam construction is the enhancement of efficiency. Traditional methods were labor-intensive and time-consuming, whereas advanced machinery significantly reduces the time and labor required. For example, the use of hydraulic excavators and bulldozers can decrease excavation times by up to 50%. At the Three Gorges Dam in China, over 200 million cubic meters of earth and rock were moved using advanced machinery, a feat that would have taken decades using traditional methods. Modern equipment ensures a high level of precision and quality control, which is critical in the construction of hydroelectric dams. Computer-aided design, CAD, software, and other digital tools allow engineers to create detailed and accurate blueprints. For instance, the Itaipu Dam, one of the world's largest hydroelectric projects, used CAD software to ensure every component was designed to precise specifications. Laser-guided machinery can follow these blueprints with pinpoint accuracy, ensuring that every part of the dam is built to exact specifications. This precision was essential in constructing the Hoover Dam, where deviations could have led to catastrophic failures. Safety is a paramount concern in the construction of large hydroelectric dams. Modern machinery and equipment significantly improve safety conditions for workers. Remote-controlled machinery allows operators to perform dangerous tasks from a safe distance, reducing the risk of accidents. At the Hoover Dam, during its construction in the 1930s, over 100 workers lost their lives due to unsafe conditions. In contrast, the construction of the Three Gorges Dam, which employed modern safety equipment and protocols, resulted in a significantly lower fatality rate. Advanced monitoring systems can detect potential hazards such as landslides or structural weaknesses in real time. For example, the Itaipu Dam uses over 2,000 sensors to monitor structural integrity and environmental conditions continuously. These systems allow for immediate corrective action, thereby enhancing overall safety. The construction of hydroelectric dams has significant environmental impacts, and modern machinery plays a vital role in mitigating these effects. Advanced equipment allows for more precise and controlled construction methods, minimizing disturbance to surrounding ecosystems. For example, the construction of the Belo Monte Dam in Brazil utilized machinery with lower emissions to reduce air pollution and protect local wildlife. Additionally, specialized equipment can be used to relocate species or create artificial habitats to mitigate the impact on local biodiversity. Technological innovations continue to drive advancements in the construction of hydroelectric dams. Drones and unmanned aerial vehicles, UAVs, are increasingly used for surveying and monitoring construction sites. These devices provide high-resolution aerial images and data that can be used to assess progress, identify potential issues, and make informed decisions. For example, the use of drones at the Grand Ethiopian Renaissance Dam, GERD, enabled project managers to monitor construction progress in real time and make necessary adjustments, improving efficiency by an estimated 20%. Advanced materials such as high-strength concrete and corrosion-resistant metals improve the durability and longevity of dams. For instance, the use of roller-compacted concrete, RCC, in the construction of the Upper Stillwater Dam in the United States allowed for faster construction times and improved structural integrity, with the dam using approximately 1.5 million cubic meters of RCC. The integration of modern technology in hydroelectric dam construction also facilitates the incorporation of renewable energy sources. Hybrid systems that combine hydroelectric power with solar or wind energy are becoming more feasible with advancements in technology. This integration allows for more stable and reliable energy production. For example, the 800 megawatts Batang Toru hydropower project in Indonesia is designed to integrate solar power, providing a hybrid renewable energy solution that enhances grid stability and reduces reliance on fossil fuels. The rapid development of China's bridge construction industry is a striking testament to the country's broader economic and infrastructural advancements over the past few decades. China's ability to construct massive, complex bridges efficiently and cost-effectively has garnered global attention and admiration. This essay will delve into the key factors driving this remarkable growth, supported by specific data and examples. Strategic national planning. A primary driver of China's success in bridge construction is the country's strategic national planning. The Chinese government has consistently emphasized infrastructure development as a cornerstone of economic growth. Policies such as the Belt and Road Initiative, BRI, and various five-year plans have allocated significant resources to improving transportation networks, including bridge construction. For instance, the BRI, launched in 2013, aims to enhance connectivity across Asia, Europe, and Africa, requiring the construction of numerous bridges and related infrastructure. Massive investment. China's commitment to infrastructure is reflected in its substantial financial investments. The country has spent trillions of yuan on bridge construction over the past 2 decades. In 2020 alone, China invested approximately 1.8 trillion yuan, about $270 billion USD, in transportation infrastructure, including bridges. Such financial dedication ensures that projects are well funded and can proceed without significant delays, leading to faster and more efficient construction processes. Technological innovation. China's bridge construction industry benefits greatly from technological innovation. The adoption of advanced construction techniques and materials has enabled the country to build longer, stronger, and more durable bridges. For instance, the use of cable-stayed and suspension bridge designs has become commonplace, allowing for the construction of some of the world's longest bridges. One notable example is the Hong Kong-Zhuhai-Macau Bridge, which spans 55 kilometers and includes a series of bridges and tunnels. Completed in 2018, it is the world's longest sea-crossing bridge and a marvel of modern engineering. The project employed cutting-edge technology, including the use of high-strength concrete and steel, as well as advanced construction techniques such as prefabrication and modular assembly. Skilled workforce. China's bridge construction industry is supported by a highly skilled workforce. The country has invested heavily in education and training programs to develop a pool of talented engineers, architects, and construction workers. Chinese universities and technical institutes offer specialized courses in civil engineering and bridge construction, ensuring a steady supply of skilled professionals. Moreover, Chinese construction firms frequently collaborate with international experts and institutions, facilitating knowledge transfer and the adoption of best practices from around the world. This collaboration has enabled Chinese engineers and construction workers to stay at the forefront of technological advancements and construction methodologies. Efficient project management. Efficient project management is another critical factor contributing to China's success in bridge construction. Chinese construction firms are known for their ability to manage large-scale projects effectively, ensuring that they are completed on time and within budget. This efficiency is achieved through meticulous planning, rigorous quality control, and the use of modern project management tools and software. For instance, the construction of the Danyang-Kunshan Grand Bridge, the world's longest bridge at 164.8 kilometers, was completed in just 4 years, from 2006 to 2010. This remarkable achievement was made possible through efficient project management and the coordinated efforts of thousands of workers. Economies of scale. China's large-scale construction projects benefit from economies of scale, which reduce costs and increase efficiency. By standardizing construction processes and materials, Chinese firms can build bridges more quickly and at lower costs than their counterparts in other countries. This advantage is particularly evident in the construction of prefabricated bridges, where components are manufactured off-site and assembled on-site, significantly reducing construction time and labor costs. Government support and policy. The Chinese government provides strong support for the bridge construction industry through favorable policies and regulations. This includes streamlined approval processes, tax incentives, and subsidies for infrastructure projects. Additionally, the government often partners with private firms through public-private partnerships, PPPs, leveraging private sector expertise and investment to complete projects more efficiently. For example, the construction of the Baithetan Bridge, one of the world's highest bridges, was facilitated by a PPP arrangement that combined government funding with private investment. This collaborative approach enabled the project to be completed ahead of schedule and within budget. Environmental considerations. In recent years, China has increasingly emphasized environmental sustainability in its bridge construction projects. The use of eco-friendly materials and construction practices has become more common, reflecting the country's commitment to reducing the environmental impact of its infrastructure projects. This approach not only benefits the environment but also enhances the long-term durability and resilience of bridges. International influence and exports. China's expertise in bridge construction has also led to international influence and the export of its construction services. Chinese firms are now involved in bridge construction projects around the world, bringing their experience and efficiency to countries in need of advanced infrastructure. This global presence has further strengthened China's reputation as a leader in bridge construction. One notable example is the Padma Bridge in Bangladesh, constructed by the China Major Bridge Engineering Company. This project, completed in 2022, is a critical piece of infrastructure that enhances connectivity and economic development in the region. The success of such international projects showcases China's ability to export its construction capabilities and contribute to global infrastructure development. The rapid development of China's bridge construction industry is a multifaceted phenomenon driven by strategic national planning, massive investment, technological innovation, a skilled workforce, efficient project management, economies of scale, government support, environmental considerations, and international influence. The country's ability to build some of the world's most impressive bridges efficiently and cost-effectively underscores its status as a global leader in infrastructure development. As China continues to invest in and innovate within this sector, its bridge construction industry is poised to achieve even greater heights in the coming years. China's bridge construction industry has gained worldwide recognition for its rapid growth, technological sophistication, and remarkable engineering feats. Central to this success are the advanced construction technologies that Chinese engineers and construction firms have developed and employed. This video section will explore the most commonly applied bridge construction technologies in China, illustrating their impact with specific examples and data. Prefabrication and modular construction. Prefabrication and modular construction are widely used technologies in China's bridge construction. These methods involve manufacturing bridge components off-site in controlled environments and then transporting them to the construction site for assembly. This approach reduces construction time, minimizes labor costs, and enhances quality control. For example, the construction of the Hong Kong-Zhuhai-Macau Bridge employed extensive prefabrication. The bridge, which is 55 kilometers long and includes a series of bridges and tunnels, required the prefabrication of massive steel and concrete sections. These sections were then transported by sea and assembled on site, significantly speeding up the construction process and reducing environmental disruption. Cable-stayed and suspension bridges. Cable-stayed and suspension bridge designs are prevalent in China, allowing for the construction of some of the world's longest and most iconic bridges. These designs use cables suspended from towers to support the bridge deck, enabling the construction of long spans over water and challenging terrains. One of the most notable examples is the Zhangyin Yangtze River Bridge, a cable-stayed bridge with a main span of 1,385 meters. Completed in 1999, it was the longest cable-stayed bridge in the world at the time. Another example is the Zaihomen Bridge, a suspension bridge with a main span of 1,650 meters, completed in 2009. These bridges demonstrate China's expertise in constructing long-span structures using advanced cable-stayed and suspension technologies. High-performance materials. The use of high-performance materials, such as high-strength steel and concrete, is crucial in modern bridge construction. These materials offer superior durability, strength, and resistance to environmental factors, ensuring the longevity and safety of bridges. High-strength concrete, for instance, was extensively used in the construction of the Baithetan Bridge, one of the highest bridges in the world with a height of 565 meters above the Baipan River. This bridge, completed in 2016, required concrete with exceptional strength and durability to withstand the extreme environmental conditions at such a height. Incremental launching method, ILM. The incremental launching method, ILM, is a bridge construction technique where the bridge deck is assembled in sections at one end of the bridge and then incrementally pushed or launched across the supporting piers. This method is particularly useful for constructing bridges over deep valleys or water bodies where traditional construction methods would be challenging. The Sidui Bridge, completed in 2009, utilized the ILM technique. This suspension bridge spans 1,222 meters across the Sidhu River Gorge, with a deck height of 496 meters above the river. The ILM allowed for efficient construction in a remote and difficult-to-access location, showcasing the method's advantages in challenging environments. Advanced surveying and geotechnical technologies. Accurate surveying and geotechnical analysis are essential for successful bridge construction, particularly in complex and varied terrains. China has adopted advanced technologies, such as lidar, light detection and ranging, and geotechnical monitoring systems, to ensure precise measurements and assessments. Lidar technology, for example, was employed in the construction of the Hong Kong-Zhuhai-Macau Bridge to create detailed topographical maps of the seabed and surrounding areas. This data was crucial for designing the bridge's foundation and ensuring its stability and safety. Digital Design and Building Information Modeling, BIM. Digital design tools and building information modeling, BIM, have revolutionized bridge construction in China. These technologies enable the creation of detailed 3D models of bridges, allowing engineers to visualize and optimize every aspect of the design before construction begins. BIM was used extensively in the design and construction of the Danyang-Kunshan Grand Bridge, the world's longest bridge at 164.8 kilometers. This high-speed rail viaduct, completed in 2010, required meticulous planning and coordination, which BIM facilitated by providing a comprehensive and integrated view of the entire project. Seismic design and earthquake-resistant technologies. Given China's seismic activity, incorporating earthquake-resistant technologies in bridge construction is vital. These technologies include base isolation systems, energy dissipation devices, and advanced materials designed to withstand seismic forces. The Human Bridge, a major suspension bridge in Guangdong Province, incorporates seismic design principles to enhance its resilience against earthquakes. Completed in 1997, the bridge features flexible cables and robust foundations that allow it to absorb and dissipate seismic energy, ensuring its structural integrity during earthquakes. Smart bridges and monitoring systems. The integration of smart technologies and monitoring systems in bridge construction has become increasingly common in China. These systems use sensors and data analytics to monitor the health and performance of bridges in real time, allowing for proactive maintenance and ensuring long-term safety. For instance, the Yavuz Sultan Selim Bridge, constructed by a Chinese-Turkish consortium, is equipped with a comprehensive health monitoring system. This system includes sensors that track structural deformations, vibrations, and environmental conditions, providing valuable data for maintenance and safety assessments. Innovative construction techniques. China has also pioneered several innovative construction techniques to overcome unique challenges. One such technique is the use of large floating cranes to install bridge sections. This method was used in the construction of the Taizhou Yangtze River Bridge, a suspension bridge with a main span of 1,080 meters. Completed in 2012, the bridge's central span was installed using a floating crane, a technique that facilitated the rapid and precise placement of the bridge deck. International collaboration and knowledge exchange. China's bridge construction industry has benefited significantly from international collaboration and knowledge exchange. Chinese firms frequently partner with foreign experts and institutions to learn from global best practices and incorporate advanced technologies. The construction of the Padma Bridge in Bangladesh, for example, involved collaboration between the China Major Bridge Engineering Company and international consultants. This partnership enabled the exchange of technical expertise and the implementation of advanced construction methods, resulting in the successful completion of the project in 2022. The Baithetan Dam, a colossal hydroelectric dam on the Jinsha River, an upper stretch of the Yangtze River in Sichuan and Yunnan provinces in southwest China, stands as a testament to modern engineering and China's commitment to renewable energy. With its 289-meter-tall double-curvature arch structure, the dam has a crest elevation of 827 meters, a base width of 72 meters, and a crest width of 13 meters. It is the second largest hydropower plant globally, trailing only the Three Gorges Dam. Equipped with 16 hydro-generating units, each with a capacity of 1 million kilowatt, the Baithetan Dam represents a significant milestone in China's hydropower development journey. Fully operational as of December 20, 2022, this project not only exemplifies China's engineering prowess but also underscores the strategic importance of hydroelectric dams for the nation's development. The Baithetan Dam's journey began in 1992 with the initial site surveying. Formal plans were laid out in 2008, and construction commenced in earnest on August 3, 2017, following the official closure of the Jinsha River in November 2014. The dam's construction period, noted for its exceptional speed, saw the completion of its first water guiding mechanism and turbine runner between 2018 and 2019. The reservoir began water storage in April 2021, and by June 28 of the same year, the first turbine started generating electricity. The project reached its full operational capacity in December 2022. The dam's impressive structure houses 16 turbines, each capable of generating 1 gigawatt, leading to a total generating capacity of 16,000 megawatts. This capacity translates to an estimated annual production of 62.44 billion kilowatt-hours, kWh, saving about 90.45 million tons of coal per year and reducing annual carbon emissions by 248.4 million tons. The dam also plays a crucial role in flood control, improved navigation, and sand blocking, further highlighting its multifaceted importance. Hydroelectric dams like the Baithetan Dam are critical to China's energy strategy and broader development goals. As part of the world's largest clean energy corridor, the Baithetan Dam joins other megaprojects like the Three Gorges Dam, Wudongda Dam, Shiladu Dam, and Shangjaba Dam. These projects collectively produce and transmit renewable energy from the resource-rich western regions to the populous eastern cities, facilitating balanced regional development and energy distribution. China's rapid industrialization and urbanization have led to soaring energy demands and significant environmental challenges. Hydropower offers a renewable, reliable, and low-carbon alternative to fossil fuels, crucial for mitigating climate change and reducing greenhouse gas emissions. The Baithetan Dam alone helps avoid burning millions of tons of coal annually, significantly cutting down air pollution and carbon emissions. Hydroelectric dams contribute to China's energy security by diversifying the energy mix and reducing dependence on imported fossil fuels. The stable and continuous power supply from hydropower supports industrial activities and economic growth. Additionally, the construction and maintenance of such large-scale projects create numerous jobs and stimulate local economies, providing long-term economic benefits. Projects like the Baithetan Dam also drive technological and engineering advancements. The dam's construction involved cutting-edge technologies and innovative engineering solutions, setting new benchmarks in the field. These advancements enhance China's capability to undertake and export large-scale infrastructure projects globally, boosting its geopolitical influence and technological leadership. The strategic placement of dams in less developed western regions of China aids in regional development by providing local communities with electricity, improving infrastructure, and boosting economic activities. This balanced regional development helps reduce economic disparities and fosters social stability. Cold asphalt concrete is a very popular and versatile material in road construction. Often used in projects such as airports, factories, parking lots, urban roads. Cold asphalt concrete production technology uses raw materials available in the country, is not picky about foundations and foundations. During construction, there is almost no loss, ensuring high product durability after construction. With great advantages: economical, easy construction, easy transportation, environmentally friendly, safe for workers and people's health, unobstructed by weather, long-term use. Today, let's learn the process of asphalt pavement construction, including the following steps. 1. Construction of the foundation layer or treatment of the old pavement. 2. Prepare ingredients. 3. Build a test run. 4. Irrigation of sticky resin. 5. Production of asphalt mixture. 6. Transportation of asphalt concrete. 7. Asphalt. 8. Tighten asphalt. 9. Finishing, maintenance. The construction of asphalt pavement involves a series of important steps to ensure a strong and durable road surface. The first step is to apply the foundation layer, which requires the surface to be within the allowable range in terms of levelness, slope, and flatness. For new roads, the foundation should be clean, dry, and flat, while for existing roads, necessary repairs and treatments should be carried out beforehand. The type of asphalt used depends on whether it is cold or hot, and it should be compacted immediately before applying the asphalt concrete. The location and height of the asphalt spread on both sides of the road must adhere to the design specifications, and altimeters are used to check the elevation. Additionally, if there are rock seams, they need to be marked and a layer of resin or emulsion should be applied. Accurate reference lines are prepared to ensure precise spreading using automatic pitch adjustment or beams as reference points. Preparing materials is the next step, which involves selecting suitable materials based on their physical and mechanical criteria. The distribution of aggregates on the cold compartment is determined, and trial mixing is done at the mixing station. Aggregate samples are analyzed for particle composition, and adjustments are made accordingly. Different resin contents are tested, and asphalt samples are molded and tested for their physical and mechanical parameters. Consultants monitor the test results and determine the appropriate resin content for the asphalt. After the preparation phase, a minimum test phase of 80 tons of asphalt concrete is carried out. This phase requires approval from the supervisory consultant based on the asphalt distribution design. Batching plants, construction vehicles, and equipment are prepared, and the asphalt is mixed and checked for quality. It is then transported, spread, and compacted according to the construction documents. Data regarding temperature, elevation, compaction, and roller velocities are recorded. After 24 hours, concrete samples are drilled to assess compaction and thickness. The results of the test phase help establish mass construction technology for future construction. In conclusion, the construction of asphalt pavement involves applying a proper foundation layer, preparing materials, and conducting a test phase. Attention to detail, adherence to design specifications, and constant monitoring ensure a high-quality road surface. The process requires careful planning, testing, and coordination among various stakeholders to achieve durable and reliable asphalt pavement. Irrigate the adhesive plastic. Depending on the type of nail and the state, the amount of adhesive resin varies from 0.8 to 1.3 L per square meter. Using liquid resin, using emulsion, 60/70 solid resin mixed with kerosene according to the ratio of kerosene to solid resin is 81/100 and watering at 45 degrees Celsius plus or minus 10 degrees Celsius resin temperature. Must be watered before 4 to 6 hours for the liquid resin to solidify, or the emulsion to be analyzed will be covered with asphalt concrete. If asphalt concrete mats are needed immediately after irrigation, hot asphalt materials can be used. On the foundation layers that have used resin, plastic penetration, asphalt screed, that have just been applied, or on the first layer of asphalt concrete that has just been spread, clean, and the Orau's warehouse only needs to water the amount of resin from 0.2 to 0.5 L per square meter. If you want to install asphalt concrete mats right away, you can water the concrete and heat it up to the construction temperature. Transporting asphalt concrete. Use dump trucks or specialized vehicles. Select the tonnage and number of cars suitable for the construction line. Transport distance ensures that the temperature of the mixture to the place of spreading is not lower than 120 degrees Celsius, usually not more than 50 kilometers. The trunk of the vehicle must be closed, clean, with a thin layer of anti-adhesive oil. Do not use fuel oil or solvents that can dissolve bitumen. Vehicles must be covered with tarpaulins to prevent the mixture from cooling down. Each vehicle transporting the mixture when leaving the station must have an ex-factory note stating the temperature of the mixture, volume and quality when the vehicle leaves the mixing station, where the vehicle will arrive, and the driver's name. Before pouring asphalt mixture into the spreader hopper, the temperature of the mixture must be checked with a thermometer, is greater than or equal to 120 degrees Celsius. Spread asphalt concrete. Only hot asphalt concrete can be spread by specialized machines. If the spreading width is too large, use 2 or 3 spreaders operating at the same time. The spreaders are spaced 10 to 20 meters apart. When only one spreader is used on a wide road surface, it must be spread according to the Soule method. The length of each segment is 25 to 80 meters depending on the air temperature. At the beginning of the working shift, let the spreader operate without load for 10 to 15 minutes. To test the machine, place under the plate are 2 dice or wooden sticks for a height of 1.2 to 1.3 design thickness of the asphalt layer. Precise value through test spread once the mixture has been evenly distributed along the spreader reel and is up to 2/3 of the reel height. The spreader begins to move forward along the specified track. While spreading, the mixture is regularly submerged 2/3 of the height of the reel. During the spreading period, it is imperative to keep the spreader compactor in operation at all times. Choose a spreader speed appropriate to the capacity of other machines in the line. Spreader speed is even throughout the spreading time. If the roller is too dotted, it should be spread intermittently. Regular dipsticks and marked iron rods should be used to check the spreading thickness. When it is necessary to adjust the spreading thickness, the sheet must be adjusted slowly so that the asphalt layer is not affected by waves or jerks. Longitudinal and horizontal joints must be well treated, and apply adhesive resin to ensure good adhesion of old and new spread marks. Vertical joints in the upper and lower layers must be soled at least 20 centimeters apart. Horizontal joints in the upper and lower layers are at least 1 meter apart. If the upper layer is asphalt layer, the lower layer is XM reinforced rock material, the joint position of the 2 layers is similar. On the road with vertical slope greater than 4%, spreading must be carried out from the foot of the slope upwards. Choose a spreader speed appropriate to the capacity of other machines in the line. Spreader speed is even throughout the spreading time. If the roller is too dotted, it should be spread intermittently. Regular dipsticks and marked iron rods should be used to check the spreading thickness. When it is necessary to adjust the spreading thickness, the sheet must be adjusted slowly so that the asphalt layer is not affected by waves or jerks. Longitudinal and horizontal joints must be well treated, and apply adhesive resin to ensure good adhesion of old and new spread marks. Vertical joints in the upper and lower layers must be soled at least 20 centimeters apart. Horizontal joints in the upper and lower layers are at least 1 meter apart. If the upper layer is asphalt layer, the lower layer is XM reinforced rock material, the joint position of the 2 layers is similar. On the road with vertical slope greater than 4%, spreading must be carried out from the foot of the slope upwards. Arrange workers to carry tools with the machine to do the following. Cover the mixture with small particles. Take it from the hopper into a thin layer along the joint. Level the protrusions and pits of the joint before compacting. Scoop. Dig out the new place where there is too little plastic or too much, and make up for it with a good mixture. Peel off. Supplement local protrusions on the newly spread asphalt layer. When it is necessary to spread streaks larger than the spreading width of the machine, 40 to 50 centimeters continuously in length, it is allowed to open the steel plate on one side of the top of the spiral wheel on the side that needs to be spread more. Manually, with rake and shovel, distribute the mixture evenly and evenly. The following rules must be observed. Use a shovel to shovel the mixture low, not from a distance, so that the mixture does not stratify. Use a rake and a trowel to spread evenly into a flat layer reaching the required horizontal slope. The thickness is equal to 1.35 to 1.45 design thickness. Manually spread at the same time with the spreader to be able to compact the machine spread with the manual spread, ensuring the road surface has no seams. In case the spreader is broken, it takes hours to repair. Immediately report to the mixing station to stop providing the mixture and use a leveling machine to spread it if HTK greater than 4 centimeters, or spread it manually when there is little asphalt. In case the spraying machine encounters sudden rain, immediately notify the mixing station to temporarily suspend the supply of the mixture. When it has been compacted to about 2/3 of the required density, it is allowed to continue rolling in the rain until the compactness is reached. When the compaction is less than 2/3 of the density, it is necessary to stop rolling, leveling the mixture. Only when the road surface is dry will it be spread again. After the rain is finished, when urgent construction is needed, the truck carrying the hot roasted sand at the mixing station 170 to 180 degrees Celsius spreads a layer about 2 centimeters thick on the road surface, collects the sand, sweeps it, and sprinkles the sticky resin. It is possible to use a steam press and a torch to dry the pavement before further spreading. For every 200 tons of mixture, take one quality test sample. Advanced countries now use asphalt transfer machines combined with spreaders. This way has the following advantages. The material mixture is remixed in the transfer machine will have uniform quality and temperature. The material is supplied regularly from the machine to the hopper of the spreader, so the flatness of the road surface is very high. Compaction of asphalt concrete. Preliminary compaction. Use a light roller to roll 4 to 8 times point. The speed of the roller should not exceed 1.5 to 2 kilometers per hour. The first roller tracks go back into the newly laid asphalt after a first round of rolling. The flatness must be checked with a 3 meters ruler, compensating for the convexity and the concavity. If spreading and rolling the sole, leave a 10 centimeters trail with a trailing trail behind. Tightly compacted. Use steam cake roller. The number of turns is about 8 to 10 times point. H equals 4 centimeters. Adding 1 centimeter of thickness must add about 30 to 35% of the number of rolls. Roll until the asphalt reaches the compaction K equals 0.98. Check with radioactive equipment before deciding to end the compaction. Finish compaction. Use a heavy-duty roller to roll 4 to 6 times point. The rolling speed should not exceed 2 to 2.5 kilometers per hour noted. When rolling, workers must regularly apply anti-stick oil to the roller. If asphalt sticks to rollers, use a shovel to scrape them immediately and re-oil them. On the other hand, use a mixture of small seeds to immediately fill the peeled area. The operation of changing direction and number when rolling must be done slowly so that the asphalt surface is not damaged, and do not stop rolling on the hot asphalt. The most effective compaction temperature is 130 to 140 degrees Celsius. The length of the compaction section, the number of rollers. Choose so that the end of compaction is not less than 70 degrees Celsius. Construction time does not exceed 2 to 3 hours. Must select lube combination for synchronization. Once this stage is over, move on to another stage. If you see that the asphalt concrete is cracked, it may be due to the following reasons. The mixture temperature is too high. Roll speed is too fast. The load is too heavy. The asphalt layer is too thin, the base layer is too weak. The asphalt mixture is not of good quality.